Hello, sorry again. Sorry, Johanna.
Hello.
So let's start this session. So are you ready?
Yes, I'm ready. Hi.
Let me introduce you. So today we are very happy to have Dr. Professor Johanna Erdmenger from Würzburg University. She's a very famous physicist doing very amazing work on the connection between ADS-CMT and ADS-CFT and condensed matter. So today she is going to talk about Kondo physics from condensed matter to holography. So without further ado, please.
Yeah, thank you very much, Valis, for introducing me, and thanks to the organizers for inviting me. It's a big pleasure. So can you hear me well?
Yes, yes.
Yeah, okay, good. So the title is what the organizers gave to me, but I think it's a very nice topic. And so let me just explain the title page. So the castle here is actually the castle here in Würzburg, which I can see from the balcony of my apartment. So it's a little town, but it's very pleasant to live here. And this is my university where I moved in 2016. And I should say that funding also comes quite a lot from this German federal science grant, which is the so-called Excellence Cluster, which is really funding research in condensed matter physics, but I'm also part of this bigger team, which is a joint enterprise of the universities of Würzburg and also Dresden. And so it's very nice that condensed matter physicists pay attention to the ADS-CFT correspondence. Okay, so let me give you an outline of what I'm going to do in these lectures. And today, in the second lecture, I plan to use my iPad. I hope this will work to give a little more detail. So now I'm going to do a little bit of an overview of this first subject, the Kondo effect in condensed matter physics, and also the Kondo model in conformal field theory. And so then in the second part today, I want to really have it more in a kind of lecture style and give you more details. So in this first hour and a half, I'm going just to introduce the topic and then give you more details as we go along. So this is the topics I'm going to cover. So first, I'm going to explain what the Kondo effect is in condensed matter physics. So I should say right away that this is a topic which has been around for quite some time, 60 years now. And it's a very nice topic because it's something which can be seen in experiment, but on the other hand, also gave a lot of impact in the theoretical developments, as I'm going to explain, like conformal field theory, the renormalization group, and all these things that these benefited a lot from studying this particular effect. And in particular, what's going to be relevant for us is that this has been studied quite a lot in the context of two-dimensional conformal field theory with boundaries. Now, for the ADS-CFT correspondence, as you probably know, we always need a large n limit. And so this large n Kondo model also has been studied by condensed matter physicists already some time ago. So I should say a little bit about that as well, because that will be very helpful for constructing a gravity dual. Okay, so this is really the more condensed matter field theory part. And then I'm going to move to ADS-CFT engaged gravity duality. And so the key point here is that we're going to use a so-called top-down approach. Then, so that means we will really use ADS-CFT at the level of D branes. So I'm sure Konrad Skram already introduced quite a lot about ADS-CFT, but I'm not sure how much he did about this top-down approach. So I mentioned a little bit about this, but if you already have seen this, then maybe you should stop me. Okay, but that will be for tomorrow anyway. And so then I'll introduce a particular holographic Kondo model, which is based on a combination of D3, D7, and D5 branes. So this was established already some time ago in 2013, my collaborators. And I show you how to use this to calculate interesting quantities in physics, like entanglement entropy, time dependence in quantum conventions, and also correlation functions. And then at the very end, I'm also going to discuss another Kondo model, which is more based on this D1, D5 range system. And so that has a lot of technical advantages, but so far we didn't use it so much to actually do physics with it, but it's still a very interesting construction. So, and that's more recent, it's from 2020. So I'm going to introduce that one to you as well. Okay, so let me thank my collaborators. And okay, there's been quite a lot of papers, and I will mention them as we go along. So I should mostly mention Andy O'Bannon, who's very decisive in this entire collaboration. And I borrowed 2 or 3 slides from him, as you will see later. And then also we work together with Carlos Hoyos. So Andy is now in Southampton, Carlos is in Oviedo in Spain. And then there was also Jackson Wu. And then my former students, Mario Flori and Max Niklas Nivcella. So Mario is now a postdoc in Madrid. And there was also some work on 2-point functions and renormalization together with Yannis Papadimitriou, whom you might know very well. And this recent second Kondo model was with Charles Mary Thompson, who's a postdoc in Würzburg, and also my student Christian Norte, but he is also a postdoc now already. So, so there was a lot of collaboration with many people, and I'm very grateful to them. Okay, so I should say, please ask questions during the talk. I think this will make it much more lively, and you know, I really would like to explain. And for me, it's very hard to gauge how much people know. So especially the students, I think you should definitely ask if you don't understand what I'm talking about. Okay, so please interrupt me at any time. Okay, so what's the Kondo effect? I mean, so it's really something which is observed in nature, so it's a real physical effect. And so what it amounts to is the screening of a magnetic impurity by conduction electrons at low temperatures. So, okay, I'm not sure if you're just looking at my slides, maybe I can also show something with my fingers, but then you have to look at me, of course. You just imagine that you have an electron with a spin, or some impurity with a spin that sits at some fixed location and doesn't move, so or some atom or ion which has a spin, and then you have this cloud of electrons around this in some conductor, and the spins of the electrons that move around actually interact with the spin of this magnetic impurity. And the most important point is that if the temperatures are lower, then there's the screening taking place. And so let me explain a little bit what the screening means. Okay, so the experimental observation is that if you have a standard metal like iron or so, and it's described by a Fermi liquid, so it's described by weakly coupled physics. Then the resistance goes like the temperature squared at low temperatures. But then, of course, you can always have impurities in your lattices, which lead to collisions of the electron moving through this lattice. But if these impurities are magnetic, then it's actually observed that the resistance actually scales with the logarithm, minus the logarithm of the temperature. And so that's a rather interesting behavior, because this means that the resistivity grows again when the temperature becomes very low. And that's rather puzzling. And so that's why many physicists studied this and tried to explain this effect. And okay, so actually how this can be seen is as follows. So actually this was very decisive in the development of the renormalization group, as I'm going to explain. And so this means if we are in the UV, which means high temperatures, then essentially we have this impurity spin, which is this red spin here. And then you have the cloud of electrons, which have these blue spins. And so in the standard Kondo model, which was established already by Kondo in 1964, we actually have just 3 electrons in this impurity spin. So at very high temperatures, there's actually no interaction in this model. Now, however, once there's an RG flow to the infrared, which means very low temperatures, then actually these electron spins align such as to hide this impurity spin, which is here in the middle. So then if you're outside this green region, you just can't see the spin anymore. And this is actually what's referred to as screening. And but actually, this is a very interesting strong coupling interaction effect. And so that's why there was a lot of interest also from the theory side. Okay, so as I already mentioned, so Kondo is a famous Japanese physicist, and he explained this behavior with a simple model already in 1964. And so I'm going to follow a lot this work by Affleck and Ludwig from the 1990s, who actually use a kind of conformal field theory language to describe this. So of course, this Hamiltonian to describe this physics can be written in a condensed matter language with creation and annihilation operators. But here I would like to stick to the more field theory description, as you can see here. Okay, so the model that Kondo actually already devised to study this physics contains fermionic fields, which are the electrons. And for a reason that I'm going to explain in a minute, they are all left movers. I will explain in a minute why this comes about. This is the Fermi velocity. And so this is just a kinetic term for free electrons. And then locally, so that's the one decisive feature of this model. So there's a delta function here. So this magnetic impurity, with which there's this interaction, just sits in the middle, and it doesn't move. And so there's this delta. And so then there's this local interaction with the magnetic impurity. So that's the spin of this impurity, and and this is the current of the electrons with some representation matrix here, which, if we are in the simplest case where this is an SU2 spin, this will be just the Pauli matrices. Okay, so here again, these are the electron fields that enter this current, and the Pauli with a Pauli matrix here, and then there's this coupling to this magnetic impurity that sits at x equal to 0. And there's a coupling constant here, which is the Kondo coupling, and it is referred to as lambda k. Okay, so this is the model proposed by Kondo. So are there any questions about this so far?
Johanna?
Yeah.
So can this local interaction be deduced from usual minimal coupling to vector field, or?
Well, at the moment, so this is a current. So it's just it's a spin, the spin current interacting with the spin impurity.
So spin impurity can be some special component of some vector field. That's a question. It looks like a minimal coupling here.
Yeah, of course, yeah. Yes, you can do this. I think that's not what people had. I mean, I think people had something much more simple in mind when this was invented, which was a long time ago. But yes, I think you can view this. Yeah, you can view this as some kind of minimal coupling. I mean, you can certainly generalize this to a more covariant form, but at the moment I'm doing something very down to earth and simple. And
the original work, yeah. Okay.
Yeah, exactly. but you're right. I mean, this can be written in a covariant way, and then you can introduce some vector field. But the key point is that, I mean, this arrow here now is it's a vector in spin space. Okay. So that's what people have in mind here. So also this arrow, this is a vector in spin space. It's not a vector in real space. But okay, I think your question is good, Jong-hyuk, because later when I'm going to do ADS CFT, actually we will introduce some gauge fields to introduce this interaction. So there will be a covariant formulation of this. So at the moment here, there's no spatial component, no Lorentz component in this interaction, but as you will see when I talk about ADS-CFT, I can write this in a covariant way. So this I'm going to do tomorrow. Yeah, so in this sense, you're absolutely right. We can also write this in a covariant way. We can also add space-time indices here, but in this simple form from 1964, this is just a vector in the spin space.
Yeah, thank you.
Okay, I will come back to this point tomorrow. Yeah, thanks. Okay, so let's just work with this very simple model. So let's imagine that we are in 1964. Okay, so no ADS-CFT. and so then this is just a vector in spin space. And so then what Kondo did was to calculate the one loop interaction term. So in this is a very simple Feynman graph where time flows in this direction. And so the impurity spin just sits here, and so it doesn't move, so it just propagates in time. Okay, so this is the dashed line. And then an electron comes and scatters, and so there's this one loop diagram like this. And so in this way, he was able to calculate resistivity. And the main point is that the resistivity gets this logarithmic contribution. So this is the Fermi energy. So we look at excitations just around the Fermi energy. This is the temperature. And so there can be antiferromagnetic or ferromagnetic coupling. So let's assume that this coupling is negative, because then we see these strong coupling effects that I was mentioning before. Okay, so Kondo wrote down this Hamiltonian, and then he did perturbation theory in this way to one loop, but he gets precisely this logarithmic behavior that is also seen in an experiment. Okay, so this is a plot from Kondo's original paper in 1964. And and this simple calculation that I just showed to you explains this logarithm minus log t behavior of, I think this was for iron with gold impurities. And so then here you see the temperature in Kelvin, and when the temperature gets lower, then the resistivity actually, this is the resistivity, increases logarithmically. Okay, so I guess these points are the measurement, and the black lines are what is obtained from this calculation that I just showed to you. Okay, so this one loop calculation explains very well this behavior of that is seen in real world conductors. Okay, so here's a slide that I borrowed from Andy O'Bannon, and so he gave some examples where this appears, and this is really very universal for lots of metals and conductors doped with many other magnetic impurities. And okay, so there's a lot of experimental progress also in the context of these quantum dots. And okay, I don't want to go into detail here. I just want to say, this is something which is very much studied experimentally and very well understood and has a lot of technological applications. And so, because afterwards I'm going to talk about ADS-CFT and brains and very complicated things, but I just want to point out that this is something which is really very well understood experimentally also. Okay, sorry. So now let's look again at this one loop result of Kondo. So this is the zeroth order contribution to the resistivity, and this is the one loop first order contribution. And then we see that there is a particular temperature scale, namely when this temperature becomes of this order, then this first order term is as big as the zeroth order term. And then obviously perturbation theory breaks down, because in perturbation theory, it's assumed that this term is much smaller than this one, okay? But due to this logarithmic behavior, if we have this relation here, then this term becomes 1, and then perturbation theory breaks down. And so the scale defines a particular temperature, which is called the Kondo temperature. And this will show up quite a bit later also in my talk. in my lectures. Okay, so, and this is a sign that actually in the infrared, when we go to low energies, the theory is strongly coupled. And so, and that motivates a lot of this interest in this model from a quantum field theory perspective, because in some sense, this is very similar to what happens in QCD. Okay, so there in QCD, there's also a scale called lambda QCD, at which perturbation theory breaks down. And so in some sense, you can view this Kondo model as a very simple toy model of QCD, because it has exactly the same quantum field theoretical behavior. And so that also motivates a lot of the theoretical interest in this model. And that will become very important later also for us. Are there any questions about this? Because this is really important.
Sorry, so this kappa doesn't have any connection with any parameter. It's just constant always?
Yeah, I mean, it's just this antiferromagnetic coupling that we introduce here. Yeah, I mean, it's just the coupling between the impurity spin and the electron current.
Kappa was not in the Lagrangian, starting Lagrangian.
Yeah, I'm sorry. I think it's related to this. My notation is not really good. I think it's related. It's just essentially related to this one up to this VF and so on. Yeah, sorry. The notation is. I have two names for the same. So essentially, it's this coupling here. Yeah, sorry for the double notation. Yeah, okay, now I'm moving to lambda again. Okay, sorry. So this is the same as this kappa now. Okay, so it's just because there's these two different names in the literature, so that's why it's a bit mixed. Okay, so now RG flows. So due to this property that I just said, that the perturbation theory breaks down, and so there's a flow to some strongly coupled behavior in the infrared. This model was studied a lot by, for instance, Ken Wilson, and in the context of establishing the renormalization group. Okay, so and the Kondo model was really decisive in the development of the RG formalism, and so this analogy with QCD, which I mentioned here, this goes even further, because now if you calculate the beta function for this coupling, so the Kondo coupling, then you see that it's actually negative. Okay, so essentially this lambda is the same as the kappa on the previous slide. I'm sorry for the confusing notation. And and this even shows even further. Yeah.
If we look at your formula for the Kondo temperature,
yeah,
that just looks like very similar to that of a BCS.
Yes, you're right. Yeah.
Right. So, yes. And in BCS there is a gap created, right?
Yes.
So now, is there any the similar concept in Kondo physics, like Kondo? Can we consider this TK not just as a temperature, but as a kind of Kondo gap?
Yeah, that's an excellent.
I never heard about any Kondo gap. So, what do you think about this?
Well, okay, it's an excellent question, because in the large N Kondo model, this really is like a superconductor. I mean, theoretically, and I will come to this maybe even this morning when I talk about the large N. So indeed, when for the large N, you can actually write this as a condensate. Okay, I will come to this maybe in 20 minutes. Okay, I hope you can wait till then.
Yeah.
And this is actually the key also of the holographic model, because then we can use holographic superconductors to describe the large N Kondo model. Mm. So in this sense, you're absolutely right. There's actually a condensation process happening there, and Now, the reason why there's no gap is probably because the fixed point is like I mean, the theory, unlike QCD, it really goes to a IR fixed point again, where you have conformal symmetry again. And that's probably why there's no gap, although there's a condensate.
When you consider condensate, do you consider Kondo lattice or just the
no, just this okay, let me jump ahead to, okay, I'm going to jump ahead a few slides because there will be okay, you see, so this is my last slide for this morning. Okay, the Kondo effect corresponds to a condensation of a particular operator. Okay, but so this can be made manifest only in the large n limit, and that's due to the fact because it's so low dimensional. So normally you don't have condensation process in 1+1 dimensions. Okay, there's this Wagner-Hohenberg theorem, but in the large n limit, this theorem doesn't apply, and then you can write it as a condensate. Okay, so I want to head to this. Yes,
yeah, I will
excellent.
Okay,
yeah, excellent question. I will. I will. It's a very good point. I will come to this, and it's really important for the holographic model that we have this condensate. Good. Okay, so the series, in some sense, is very similar to QCD because in the UV, there's in the UV fixed point is just a free theory. So we have some kind of asymptotic freedom, like in QCD. And then here I say in some cases, which depend on the representations chosen for the spin of the electron and the impurity. But so the difference to QCD is that the model really flows to a strongly coupled infrared fixed point. And so this means there's conformal symmetry again at this fixed point. And that implies, I think, that there's no gap. And okay, and in this way, this model is much simpler than QCD because it is, I mean, you can actually show that it flows to an infrared fixed point. I know some people who study QCD, they also assume that that QCD has a strongly coupled fixed point in the infrared, and there's a lot of work on this, but there it's still at the level of a conjecture, whereas here you can really calculate because the model is so simple. Okay, so in some sense it's similar to QCD, but it's much simpler, so we can do much more than in QCD. Okay, so this is another slide I borrowed from Andy. So there, due to all these nice theoretical features, many people in the 70s and 80s studied this model, and it really made helped to make a lot of progress in theoretical physics in understanding quantum field theory. So one was the RG and also numerical methods, as I already mentioned. Then you can describe this as a Fermi liquid with this boundary term. Then there's also a solution of the Kondo model using the beta ansatz and integrability, which is also very interesting. And then, as I will come to, you can also consider the large N expansion. So far I talked about electrons and spins that have spin a half, okay, but we can also take a spin with many more components and consider a large N expansion. Then this can also be used, studied using quantum Monte Carlo. And then there's this beautiful series of work on boundary and conformal field theory that was established using this model. And I'm going to tell you a little bit about this because if we want to do ADS-CFT, then obviously conformal field theory plays an important role. So this is just to show that you know, this was model, and this is a super nice model because it describes something which is really there in experiment in nature, but on the other hand, it really had a big push on lots of developments in theoretical physics as well. Okay, so and there's a number of generalizations that can be made. So first is to enhance the spin group, go from SU2 to SUN, and this is certainly something we have to do if we want to do ADS-CFT because ADS-CFT only works if n is very big. And then one can choose different representations of this impurity spin. So rather than have a spin 1/2 representations, we can take more general representations. And then we can also introduce a flavor symmetry. Okay, so if this is the creation operators in our field psi, we can take several of them and have an additional SUK symmetry. And so in particle physics, this would be called a flavor global symmetry. And in condensed matter physics, this is called a channel symmetry. But I mean, mathematically, this is exactly the same as a flavor symmetry. So these are possible generalizations. And so that brings me already to the CFT approach. Okay, so as I said, I mean, Affleck and Ludwig really had a lot of developments in the 1990s, by which they actually solved this Kondo model using CFT techniques. And so first of all, one can reduce the problem to a 1+1 dimensional problem. And so this is due to the fact that if we have only one impurity sitting at the origin, then obviously there's a spherical symmetry, and we can do the so-called S-wave approximation. This means, so normally we have components time and then X, Y, and Z if we are in 3-dimensional space. But if we neglect these angular dependencies, and so this is which is called the S-wave approximation, then we only need to worry about the radial component and also time, of course. Okay, so then if we introduce polar coordinates, then we have a radial component which goes from 0 to infinity and time. And so then this reduces really to a 1+1 dimensional system, but there's a boundary when R is equal to 0. Okay, and now to do conformal field theory, there's a trick which is to consider only the left movers. Okay, so what I described so far is written here. So here we have now this radial direction. This is our impurity spin that sits at the origin, and then this provides a boundary. And but then since we have free electrons in the UV moving around, we have right and left movers here. And so now there's a trick of using some analytical continuation, which is to continue the radial direction to negative values, and at the same time consider the right movers to just be left movers, which move at in this negative radius direction on this side of the impurity. Okay, so it's a way this arrow is just flipped over to the other side. And then we arrive at this chiral model where there's only left movers. And that simplifies a lot the computation. And so this is achieved by introducing these negative values of the radial coordinate. Okay, it's just some calculational trick if you want.
Oh, that is a little bit confusing.
Yeah.
Because are you saying that in this one-dimensional problem, there is no reflection or no backscattering?
Well, there's an interaction here, of course, and there, you know, there will be it's like a defect, so there will be certainly things happening there. Right. Yeah.
Then how do you describe the backscattering, this deflection or whatever?
Well, okay, this is exactly what I want to show to you. I think I will answer the question. I mean, okay, so this picture allows to write the Hamiltonian in the way. Let me go back to where I wrote the Hamiltonian for the first time. Here, okay, so as you see here in this Hamiltonian, there's only left movers here. Okay, but these left movers, of course, interact with this impurity, and so I mean the backscattering really then, if you do this approach that I just showed, then the backscattering really means that you have things that move to negative values of the radius, which, physically is not there. Okay, so it's like having a particle and an antiparticle. So an antiparticle is a particle that moves backwards in time. And now you can say, a backscattered particle is a particle that moves at negative values of the radius. Does that make sense?
Proceed.
Yeah. Okay, I think there will be more details, then we can come back to this point. Okay, let me go back to where I was. Okay, so let me give you this essence of this approach of Affleck and Ludwig, and I will give more details later. Now, okay, so the key point of this Kondo model is that really this calculation that I showed to you leads to an infrared fixed point. Okay, so there's again a conformal field theory in the boundary theory. Okay, and so the difference then between the UV and IR will be precisely the boundary conditions at the defect. So this is the essence of this approach of Affleck and Ludwig, and they build the representations of this infrared conformal field theory from the representations that are there in the UV. And so the idea is to compare the CFTs at the UV and IR fixed points. Okay, so now psi minus and psi plus essentially will be the left, so psi plus will be the left movers on this side, and psi minus will be the left mover on that side where there's negative values of the radius. And then, of course, at this defect here, there needs to be a boundary condition then. So in this sense, this leads really to a boundary conformal field theory construction. And so in the UV, the electrons, the fermions, they're just free. Okay, so if they're free, this means they don't interact with this impurity and they just move through. Okay, so they just in this picture they just continue moving and they don't notice this red arrow sitting here. And so then obviously if they don't notice anything here, then you need a trivial boundary conditions, which means the field moving on the left-hand side of the defect is the same as the field moving on the right-hand side of the defect. And so this is the boundary condition at r equal to 0. Okay, so and as I will explain in further detail as I move along, in the infrared, the boundary condition is that there will be a phase shift here. Okay. So then actually the interaction at this point amounts can be translated into a boundary condition, which means that so the effect of this interaction of the spin will be that this particle which arrives here gets a phase shift of 180 degrees when it passes through this point. Okay, so this is this result of Affleck and Ludwig, and I will show you more details in the second hour today.
So
okay.
In terms of reflection, the free case is just reflect with the phase rotation.
Yes, exactly.
And then the spin also doesn't change. Yeah, spin up down doesn't. You don't distinguish here. There is no.
Exactly. Yes.
Okay.
Hello, Professor.
Okay. Yeah.
Hello, Professor. I do not understand why the energy scale will change the boundary condition. When you do the RG flow, why the boundary condition will be changed?
Okay. Okay, very good question. Okay, let me backtrack. Okay, so let me go back to this picture. so in the UV, everything is free, okay? And in the infrared, there's this screening happening. Okay, so that's the physical picture. And now let me go to the calculation again. Okay, so this is this one loop calculation. And so in the infrared, there is the theory is strongly coupled, which means that there's a strong interaction between the spin and the impurity, the impurity spin and the electron spin. Okay. So the statement of Affleck and Ludwig is that this interaction in conformal field theory language only amounts to a change of the boundary condition. Okay, so so the statement is, in the UV we have a free theory, which is a conformal field theory, and in the infrared we have another conformal field theory which is strongly interacting. And the strong interaction then in the CFT language can be written as a change of the boundary condition. Does that answer your question?
Yeah, a little, but now I want to ask, what is the Barker interpretation?
Sorry, what is
the Barker interpretation? How do I understand this boundary condition from the geometry?
Okay, I think I'm still in the process of explaining. I mean, okay, so at the moment I'm just making the statement that from conformal field theory, I'm just stating the result from conformal field theory, which is that the strong interaction amounts to a shift in the boundary condition.
Yes.
At the moment I'm just telling you this, but in the second hour today, I want to explain this in much more detail. And actually, I will use my iPad and write down the calculation, and then I think I will answer your question then. Okay, so at the moment I'm telling you this, but as you say, it's very important to understand how this interaction translates into a boundary condition, and this is what I want to explain later this morning.
Thank you.
Yeah.
Thank you.
Yeah, thanks for the question. Yeah, very good. Okay, again, so here I'm just giving you an outline of more detailed things that I'm going to show you in the lectures. But these are of course the very important features. Okay, so in the infrared, okay. This is just a statement which I haven't proven now, but I will do later. Okay, so I'm just telling you now, the interaction amounts to a phase shift of this form. And this is a boundary condition that you have to impose in this particular location.
By the way, for your notation, psi plus means psi, right? And the psi.
Yeah, okay, so yeah, well, psi plus and psi minus are the boundary values when I approach this point. Okay, so psi plus is when I come from this side, and psi minus is when I come from this side. So psi plus is the value of these fields at r equal to 0, and psi minus is the value of those fields at r is equal to 0. So that's why this is a boundary condition. I mean, this condition holds only when r is equal to 0. Okay, it's just a way of writing a boundary condition.
I'm just asking about the definition of psi plus, psi minus in terms of psi left and psi right.
Yeah. So psi plus is the fields on the right-hand side of this impurity in the limit where r is taken equal to 0. Okay, so I should write down. I mean, okay, I will have my iPad in a second. So it's just, this statement here is just a statement for r is equal to 0. And psi plus are the fields on this side of the defect, and psi minus are the fields on that side of the defect. Okay. And then of course from both sides I can take the limit of taking r equal to 0. and that's where I impose the boundary condition.
Okay.
Yeah, so psi plus is just the value of taking the limit r going to 0 from positive values.
Yeah, yeah.
And,
so plus
and
means
psi
0
minus is
plus
taking,
epsilon. Okay.
yeah. Yes.
Hello.
Yes.
Could you show one L-log phenomena from QCD for the change in the boundary condition?
Sorry, can you just repeat the question? I didn't understand.
Because in this system you can change the boundary condition by
Yes.
the energy scale, but you also say that this model is similar to QCD. But
Yes.
could we see some similar example from QCD?
Okay. Well, okay. The model is similar to QCD in the sense that it's strongly coupled in the infrared. Okay, but in this model, we know much more than in QCD because it's much simpler. Okay, so as in QCD, this model is strongly coupled in the infrared. But on top of it, we know that in the infrared, there is a strongly coupled fixed point. Okay, and that's why we can use all these methods of CFT.
Okay.
In QCD, it's not known what happens in the infrared. I mean, apart from the fact that there's strong coupling. Some people believe that in QCD, there's also a conformal fixed point in the infrared, but there it's impossible to actually prove it. Okay, but here, because it's just in 1 + 1 dimensions, we can do much more. And it can be explicitly calculated that the beta function just vanishes.
Sorry, maybe let me. I'm just wondering if we have this phenomena for change the boundary condition, what should we see in the hadron scale?
If there, okay, you say if we had the 6 point, what should we see for the hadrons? Yeah, very good question. So maybe let me just say what we see here, and then we can think about what we would see for the hadron spectrum. Okay. So let me just quickly say what we see for the Kondo model. So, so exactly as you just said, in the Kondo model, this change in the boundary condition induces a change in the spectrum. Okay. And essentially you can, okay, because another thing is, okay, so why it's hard to answer your question is again that here, because we are in 1 + 1 dimensions, okay, so a conformal field theory has an infinite amount of symmetries. And we can all use the structure like the Virasoro algebra and all these things. And so using this Virasoro algebra, we can write down essentially the entire spectrum of this conformal field theory. Okay. And so we have these infinite towers of representations. And then what Affleck and Ludwig do is they actually just so-called fuse these representations. Okay, so which means that they use techniques of conformal field theory to build new representations as a kind of tensor product or using Clebsch-Gordon coefficients and of the spectrum. And of course here we also have something similar to mesons, okay, because there is a bounce. So this bounce state, okay, let me just show my bounce state again. So this state here is really a singlet state where you have a singlet made out of this impurity spin and one electron spin. I will show this later this morning. And so we really have a meson, okay, made out of, if you want, an impurity spin and an electron spin, and this you can see is a bit similar to a meson in QCD. Okay. Like, I mean, of course, a particle which doesn't have spin, like.
But by the way, Johanna.
Yeah.
I guess that I wasn't very sure whether this conformal field theory can capture the creation of a scale, like Kondo temperature?
Okay, yeah, good question. Okay, let me go back to okay, so okay. Okay, so I think this temperature really happens in this perturbative picture. Okay, so Kondo in 1964 just used perturbation theory. Okay, so he calculated this one loop diagram. Okay, and then
yeah, right. So what I'm saying is that after below this Kondo temperature,
yeah,
theory is in some other phase, so that I don't think conformal field theory can be applied.
Well, but okay, so as I'm going to show it to you, okay, I haven't given you any formula yet, but as I'm going to show to you, here you can really show that in the infrared there is a fixed point. And this is different from QCD because there we don't know. Okay. And so I think this is two different stories. Okay, so this is the story. If I use perturbation theory, I realize that at some scale my theory becomes strongly coupled. Okay. So that's similar to QCD. But now here on top of this, I can show that if I go to really zero temperature, then I reach a fixed point again.
So by the way, I haven't followed it closely, but does I mean the Affleck
yes
have the concept of Kondo temperature?
Yes, yes, they do. But of course, as you correctly say, I mean, within the QCD, it doesn't play such an important role because, sorry, in the CFT, it doesn't play such an important role because there you just go to zero temperature, essentially. You go to the
yeah, you
point.
see that the QCD is the conformally invariant, but the meson theory and the hadron theory doesn't have any conformal invariance, right?
Well, that's just the question. I would say we don't, I mean, to be honest, we don't know. I mean, in QCD, we just don't know what happens if you, to this theory. And there's some people who believe that also QCD has a...
Of course, I mean, the lambda QCD means the scale symmetry is broken. That means there is no conformal symmetry.
Yes.
If this is an analogy, the same thing should happen. That is below lambda QCD, sorry, I mean, below Kondo temperature, conformal field theory shouldn't apply.
Well, but I will show you here that we do get a fixed point. And this is different from QCD. So, okay, I think what you say is very much relies on this perturbative picture. Okay, and of course in QCD, you're entirely right. If we sit exactly around this lambda QCD, then obviously the theory is not conformal. But it's not clear that if you go to even lower scale, QCD will not run into another fixed point. I mean, there are some people who really seriously study this. Okay.
You are not. Did you say that the exact result Kondo temperature is zero?
No. The Kondo temperature is given by this.
Okay.
But
IR fixed.
If we look at CFT, we go to zero temperature. But then it doesn't mean the Kondo temperature goes to zero, but just the ordinary temperature goes to zero. Okay, so I mean the Kondo temperature is where this rise starts to happen. Okay, but then if we go to CFT, we just go there. Okay. So the Kondo temperature is like lambda QCD, but the CFT picture really goes if you take your scale all the way to zero, which doesn't mean that you take the Kondo temperature to zero. It just means you take the temperature to zero. Okay, was this clear?
Okay, yeah. And that zero temperature is IR fixed point.
Yes, exactly. Yes. precisely. Okay, so let me say again, in this perturbative approach, this model looks very similar to QCD, but the difference is that in this 1+1 dimensional case, we have a non-perturbative approach which we can use below the scale, and which tells us that we have this infrared strongly coupled fixed point. Okay, and the fact that we have this non-perturbative approach is due to the fact that we are in 1+1 dimensions, and then we can use all these techniques of 1+1 dimensional CFT using Virasoro algebra and so on. Okay, if we are in QCD, because we are in 3+1 dimensions, so as Dong Hyuk knows very well, in 4 dimensions, the conformal group is finite. Okay, so there's not this mathematical structure where we know the entire spectrum of the field theory just from the symmetry. That's the difference. Okay, so and this is the things we can't do in QCD yet. Okay, just for the fact that we don't have this infinite conformal symmetry in 3+1 dimensions. Okay, I hope that at least partially answers all the questions that were asked by various people in the last 10 minutes, which were very good questions. Okay, is there any other question about this? This is quite important.
Sorry,
okay.
if you
Go ahead.
If you break the chirality and you only have left moving modes, then is it better to, instead of using Virasoro algebra, we use Katsmoody algebra? Because Katsmoody algebra.
Exactly. Yeah. Okay, so there will be Katsmoody algebras. There will be lots of Katsmoody algebras appearing in the next slides. Yes, exactly. So we will have because we have additional symmetries in addition to the conformal symmetry, then it's natural to have Katsmoody algebras. I will show you Katsmoody algebras coming up soon. Yeah. Yes, they play an important role, and in particular, since we have these Katsmoody algebras, we know what the spectrum of our theory is. Okay, and then we can obtain this. So basically, the work of Affleck and Newton was to use these Katsmoody algebras to obtain the spectrum at the IR fixed point. Okay. Yes. Here, there are the Katsmoody algebras. Okay, so this is my next slide. So this is a very good question because I'm coming to this now. Okay, so so this is the difference to QCD in here, because here we have this infinite dimensional symmetry, so we can use these Katsmoody algebras to determine the entire spectrum. And this is just what we don't have in QCD. So I cannot really answer what happens to the spectrum in QCD, assuming that there's a fixed point, because I don't have these techniques available in more than 1+1 dimensions. Okay. Okay, let me go on. So let's assume that we generalize our model, and so we don't just have an SU2 spin, but an SUN spin. And then we take several flavors of electrons, which are called channels in condensed metaphysics. And then we have SUK flavor symmetry. And then because the electrons are also charged, we have a U1 charge symmetry. Okay. And for this symmetry, we can now write a so-called Katsmoody algebra. I will explain this also in more detail in the next hour. So then, so this means we have an SUN symmetry of level K, and an SUK symmetry of level N, and then this U1 charge. So what does it mean level? Well, okay, so because we are in a conformal field theory, we can expand the currents in our model in terms of a Laurent series. And this is just an analog to the Virasoro algebra. So we have coefficients for the various coefficients in the Laurent series in our algebra. And then we have this infinite dimensional algebra. So okay, this is a kind of standard algebra, but then we have an anomalous term here. And the anomalous term has a coefficient which corresponds to this level in the symmetry. So this k is the same as this k. Okay, I will also explain this in more detail coming up. Okay, so, and now there's a technique in 1+1 dimensional conformal field theory, which is the so-called Sugawara construction. And which means that we can separate the spin, channel, and charge currents. So we have a conserved current for each of these symmetries. And so they can be written in terms of the fermions, of the electrons. I will also show this to you soon. And so then we can write our Hamiltonian. So this is the same Hamiltonian as the original Hamiltonian that I had. So, oops, where was it? This Hamiltonian, but this Hamiltonian was just for spin a half. But now I can take an SUN spin, and I take k flavors of these electrons, and I'm also aware that these electrons they are charged. Okay, so this gives an extra U1 symmetry. And then I can rewrite the Hamiltonians in terms of the currents. And this is done here. Okay, so this is again my Hamiltonian. N and K are these numbers that appear here. And then here I have one current that only contains the spin symmetry, one current that corresponds to this flavor symmetry, and one current that corresponds to the electromagnetic symmetry. And okay, I will write down how these can be written in terms of the psi left that we have. Okay, and so this is a technique which is inspired by current algebra, which is also a technique which is famous in QCD also, but here again we are in 1+1 dimensions, so we have this infinite amount of coefficient in this Laurent series. And okay, so this is essentially just a rewriting of the Hamiltonian in terms of new variables, and then the interaction term with our Kondo coupling can then just be written as an interaction of this spin impurity with the spin current. Okay, so this J with the vector is the one from the spin here at the front. Okay, so I can also write S little a, J little a here for the scalar product. Okay, so this is our Hamiltonian in the ultraviolet. Okay, I will give you more details how exactly these J's are defined and what a Katsmoody algebra is and so on. But, so at the moment, the only thing you need to know is this is a rewriting of the generalization of this Hamiltonian that I wrote at the very beginning. And we have this interaction term of the spin impurity interacting with the spin current that I now have written here. Okay, so now this is actually the way that this infrared fixed point can be written explicitly, because as Affleck and Ludwig showed, we can now redefine the spin current. So we define this curly J, which is the original spin current. Okay, so it's this current here. And then to this current, we add a contribution which involves this spin impurity together with this Kondo coupling, and it's only defined locally where x is equal to 0. So, and if we have this, then it can be shown that if this lambda takes a particular value, which is this value, okay, definitely fixed, so a definite fixed value. If we do that, then we can actually rewrite the Hamiltonian again in such a way, so where now this original straight J is replaced by this curly J. So this means if we go to our UV theory, we just absorb this term into this term by redefining the J. Okay, we can redefine the spin current in such a way that the interaction is absorbed into this current. Okay, and then I can rewrite this Hamiltonian, which has this interaction, in terms of that Hamiltonian, where the difference is that now I have this curly J, this one, okay? And so this means if I do that, then I kind of have hidden the impurity. Okay, so now suddenly it looks like a free theory again, okay, like a conformal field theory. And the impurity is kind of hidden in this term here. So, but then formally again, I have a free theory, and this will correspond to my theory at the infrared fixed point. Okay.
Hello, Professor.
Yes.
If you take a larger limiter,
yes,
then what is the Hamiltonian for the S equal 0?
Yeah, okay, that's a very good question. Obviously, if you take a large n limit, then it doesn't look very good. But I will show to you that if in the large n case, we start from the beginning with a totally different technique. Okay, so I agree with you that this only makes sense if n is not too big. Okay, I mean if n goes to infinity, then this is not very meaningful. But I will, in the case that n is very large, we can do something else, and I will show to you in a second. I will give you an outlook.
I just guess that when you use the larger limiter, you ignore the delta 0, so hence you can get a free theory. It's like some you remove some, you relax some singularity. I guess that you will do that. Is it correct?
Well, I think this works for any n.
Yes.
Okay, I mean, but they have extracted this.
But when x goes to 0, indeed you have an infinity over infinity. So I guess that when you later delta 0 become as the delta epsilon, it's not really 0. So in this sense, when you take a larger limit, you will get a free Hamiltonian. I guess you take some this kind of approximation to do the calculation.
I'm not sure. Okay, we will come back to it in the second hour. But I am pretty sure that this construction works for any value of n and k. I mean, that's
okay. I do not say it's not correct for any, and I just said how you take the limit. It's a different question.
Yeah. Okay. So let me say that. Okay, I will talk about large n on the next slide, actually. so let me make one final comment about this. So okay, here let's for now just assume that n is finite. Let me just explain what I wanted to say here, and then I will talk about large n, because in large n case the whole people do something completely different, which I will show to you in a minute. Okay, so
Johanna?
Yeah. Yes.
Was there any argument why we can neglect the delta squared x and
yeah, good. Yes, I think there's an argument why we can. Well, I mean that would be some kind of ultra local term, and then yes, okay, it's a good question, but I mean there are some arguments why you can neglect the square term in this. Well, okay, I guess it's some kind of regularization argument, because if we have a square of this, yeah, it's okay. So it's a term which usually appears in quantum field theory, and then you just say, okay, that's subtracted because it's a contact term and not very well. I mean, it's divergent contact term and so on. So and there's some quantum field theory argument why you don't have to take the square into account. Okay. Okay, the point I wanted to make here is, so that's what Affleck and Ludwig do, is that they use now some conformal field theory techniques to calculate the shifted spectrum. So because in a CFT in 1+1 dimensions, the spectrum of the theory is entirely known. So this means we can now use this fusion techniques, as it's called, okay, in CFT, and write the representation of the infrared theory in terms of a kind of Clebsch-Gordon expansion of the UV spin representations and this impurity spin. Okay, so the new spin is a kind of combination of these two things, and that also translates into the fact that then the representations will be combined in a particular way. Good. Okay, but let me. Okay, before I come to the large N, maybe let me say this thing. This is another important thing I have to say. So now if we allow the impurity spin and the number of flavors to be different from spin a half and one flavor, then there's different kinds of screening. So there's critical, under, and over screening. So if we have critical screening, then that's what I was talking about all the time. So just look at my fingers now. So we have two spins, the impurity spin and the electron spin are of the same magnitude. So if we form a bound state, then we just get a spin 0. Okay, so and then essentially we don't see this impurity anymore, and there's total screening. But now there's also something called underscreening and overscreening. And the underscreening is if the impurities, twice the impurity spin is bigger than the number of flavors, because then, you know, there's some, the impurity is not totally screened. And then we just recover the same as in the UV, but with a slightly smaller spin representation. Okay, so that's called underscreening. And critical screening is what I explained all the way along. So then if twice the impurity spin is just equal to the number of flavors, then we get K-free left movers. So that's what I was explaining before. And then there's also something called overscreening. This means if there's more flavors than twice the impurity spin. And then something really complicated happens because you know, there's more electrons coming to this impurity spin than really needed to screen it, and that's some very non-Fermi liquid behaviors, which is of great interest to condensed metaphysicists. Okay, so these are three different behaviors that we have to keep in mind can exist. But I think they can all be studied with these conformal field theory techniques. So I just wanted to introduce these terms, critical, under, and over screening. Okay, and then finally, let me say a little bit about large N. Okay, so in large N case, actually something quite different is done. And so let me just give you an outlook here. And this we will talk about a lot because in the ADS-CFT model, we have large N, and we will follow exactly the procedure that's given here. Okay, so if we consider the spin of the impurity and we have an SUN spin, and now look at a representation of this large N symmetry which describes this spin, then we get the group theory representation will be a Young tableau with Q boxes. So it's a totally antisymmetric representation. And so then the Young tableau was just like a ladder of boxes. And so what can be done in this case, which is not really possible if N is finite, is that we take this spin operator, this impurity spin, and we write it as hyperlinear in the so-called slave or aprecursive auxiliary fermions. Okay, and then this matrix, so this used to be the Pauli matrix before, but now we take a much more complicated matrix of a representation of SUN, which is a totally antisymmetric representation. And then essentially, sorry, we write the spin as a bilinear in these auxiliary fermionic fields. Now if we do this, of course, we introduce more symmetries than there were beforehand because there is a spurious U1 symmetry that we introduce. Okay, because if we write it like this and we perform a rotation on chi and the inverse rotation on chi dagger, then this is invariant. So we introduce a U1 symmetry which wasn't there before. And so we need to fix the symmetry if we want to have the same amount of degrees of freedom as before. And this is fixed by imposing that the charge density of these new fermions should be equal to some number, which is called little q. And it's related to the number of boxes by this relation. So the number of boxes is little q divided by n. Okay, so now what's the advantage of this? Well, the advantage is that if we take n to be very large, then we can write our Kondo coupling as a so-called double trace deformation. It's a bit misleading because here fields are in the fundamental representation of the group, so there's no trace. So then also there's no double trace. But what this means is that we get two contributions that are separately invariant.
Johanna?
Yeah.
Could you small q is a large number, you say?
Yeah, I mean, you can take it to be large, but you can also take it to be small.
Chi is sitting only at the boundary?
Yes.
At 0?
Yes.
And
correct.
That is just a large number.
Yeah, I mean, you can take q to be large, but you don't have to. You can also take q to be small. I mean, the important thing is that n is large. But then you can always adjust little q to
you
take.
say that the q is a number of a box.
Yeah, this is the number of boxes, yeah.
Therefore, if n is large, then small q should be very large.
Yes. But okay, maybe I was a little imprecise before. I mean, this capital Q doesn't necessarily have to be large. I mean, you can also take it to be a small number. So you can also take little q to be of order n.
So this is probably what you mean is that this expectation value of chi theta chi is a small q, which is very big.
Yes.
Okay.
Yeah.
All right.
Okay. So now the interesting thing is, if we are in the large n limit, we can rewrite so here I wrote the interaction. So this spin current is something which looks like this, made out of these left moving electrons that we discussed all the way along. Okay. And now I'm writing this spin operator in this form.
May I ask a question?
Yeah, sure.
Can you hear me?
Yes, yes.
Okay. Maybe I forgot your point. Why do you take a totally anti-symmetric representation for the S? I think I missed the point.
Well, okay, it's just to have this interpretation as a spin operator, I think, and because these objects are fermions. Okay, so if these objects are fermions, I think you have to make it totally antisymmetric. Okay, so this is a fermionic field. I think that's the point.
Of course, yes.
Yeah. So this is a fermionic field, and then to have some meaningful spin interpretation with this fermionic field, you have to have a totally antisymmetric representation. Okay, and but then the point is, this interaction now can be written in this way. Okay, so here, this is what we had before already, our spin current. So this is the same as I was discussing for the conformal field theory. This current, okay, so in this current can just be written in terms of the electron fields and this representation here, so which then you take to be the same as that one, okay, and then here I just use what I just introduced. I said, okay, let's write the spin operator in terms of a bilinear of fermions in this way. Okay, so now the key point, if n really goes to infinity, So I can at any n I can use a Fields identity to evaluate this product of these two matrices. But then if n goes to infinity, lots of subleading terms go away. And the only terms that are left is essentially this product of two scalar operators, O and O dagger. And this operator O is essentially a bilinear made out of an electron and one of these slave fermions. Okay. And now this is called double trace because each of them are separately invariant under the various symmetries of the problem. And it's a singlet of this SUN symmetry while it remains charged under the remaining flavor and level and charge symmetries. And what's also important is that the dimension of this field is a half. And so, okay, the key point is that, okay, here I have an interaction between two vectors in the spin space, but in the large n limit, I can translate this into an interaction between two scalar fields, which in analogy to what happens in ADS-CFT, I can call double trace because each of them is individually invariant under this SUN symmetry. And so that's why I call it double trace, okay, although there is no trace here. Because both of these fields are in the fundamental of this SUN symmetry. Okay, but this is now going to be the key also for the ADS-CFT realization, because also in ADS-TFT, there are some methods for switching on the so-called double trace deformation, which I will show to you. Okay. And and now to come back what Sanjay asked before, it has been shown, so these are condensed metaphysicists, and so this is already 20 years ago, this paper. So the Kondo effect in this case corresponds to a condensation of this particular operator. So then, so it means that now our flow from the UV to the IR will be triggered by this double trace operator. And and at this infrared fixed point, there will be a condensation of this operator happening, okay? And it's a mean field transition, okay, which, okay, again, let me be careful because normally in 1+1 dimensions, you cannot have, or even in 0+1 dimensions as we are now at the defect, you cannot have phase transitions. However, that argument, which is this Mermin-Wagner theorem, does not apply when n is infinite, okay? Because then long range, I mean, there's, fluctuations are still suppressed. So this argument why you can't have phase transitions in low dimensions is because the fluctuations ruin the phases. But in the large n limit, these short range fluctuations are suppressed, and there's only long range fluctuations, and then you can still have a phase transition. And then the Kondo effect corresponds to this condensation. And this is exactly what we're going to have in the ADS-CFT model. So we can use a so-called holographic superconductor where there's a field dual to this operator O. So we can really design all the symmetries to be in such a way as we want them to be. And then we can see this condensation. Yeah.
This operator is not invariant under this additional U1 symmetry you talk about.
No, exactly, because the condensation spontaneously breaks this additional U1 symmetry. Yeah. Okay, so if it's a superconductor or a superfluid, it needs the spontaneous breaking needs to break some symmetry, and it's precisely this additional U1 which is spontaneously broken by the condensation of this operator.
Okay. And also because J is bilinear or quadratic in psi, your Hamiltonian will be quartic in psi, and it doesn't look same as the original Hamiltonian. I'm a bit puzzled.
Why? No.
You have a J square in the Hamiltonian, so there will be a quartic in psi.
I'm just rewriting this operator, the interaction term.
Yeah, but I'm talking about J square term in the Hamiltonian.
Yeah, but I don't. I mean, this only applies to the term where there's this S. I don't do anything to the kinetic term.
Yeah, but the Hamiltonian has J square. Yeah.
I see what you mean. Okay, but this is already in the Sugawara construction. Okay, I will come back to this in the next lecture because I'm going to write how to get this current. Okay, that has nothing to do with the Kondo model. It's just a conformal field theory approach. Yeah, it's a good point. Let me explain this the next lecture. Yeah.
Johanna.
Yeah.
What is this U1? Charge?
Well, this is just an extra sim. So if this is some operator, okay. If I take this operator and I write it in a bilinear of fermions, then I get an extra symmetry.
Yes.
Extra symmetry is because I can rotate this by a phase and this the opposite phase.
Great.
Yeah, and so then I introduce a symmetry which was not there before. So in my Hilbert space, I have more degrees of freedom as before, but this cannot be.
So that is not the charge, you say?
No, it's not a charge. It's an additional spurious U1 symmetry. Yeah.
And you are fixing.
Yeah. I'm fixing the charge density to keep the same amount of degrees of freedom. But nevertheless, the symmetry is, this is again invariant under this new symmetry. And then if there's condensation of this operator, this new symmetry gets spontaneously broken.
If chi and the psi is transforming, so you say the psi is not transformed under that U1? So.
Yes, exactly. So that's why this thing breaks the symmetry.
But I think that is it true that the this is the psi is the SU, not U? Is that the point?
I'm not sure. So SUN is the symmetry group of the spin. Okay. And then I get an extra U1 because I introduced these chi's. But then if there's a condensation, this extra U1 gets broken. But what I have to make sure is that this operator is a singlet of the original SUN symmetry. And that's indeed the case, okay? Because under this SUN, so this is in the anti-fundamental and this is in the fundamental of this SUN. So this is a singlet of the SUN, but it breaks the U1, this new U1.
So which representation chi belongs to? In SUK times UNF times U1. So what is the
so it's in the fundamental representation of SUN.
Right.
And
SUN, there's no U1 in chi.
No, but this U1 is an extra U1. It has nothing to do with this SUN.
But you just told me that chi belongs to SUN, not UN. So you cannot.
No. But there's different. Okay, so there's SUN is the spin symmetry. Okay.
Okay.
And then there's an extra U1 which has nothing to do with this SUN,
there is
which is
extra
just a fact.
Okay.
Yeah.
But then what prevents you to just to have the psi? You don't have such a degree of freedom in psi, you say.
Okay, there is this SUN symmetry, and this is a representation of SUN. But the U1 has nothing to do with this SUN. Okay, it's just
But I thought that it is just a little bit confusing that why only chi should have such a luxury to have extra U1.
Can I make a comment on this point?
Yeah, sure, go ahead. Yeah.
I think that just to help Chang Jian's understanding, here chi is not free fermion, it's a highly constrained because the chi dagger chi is equal to q. So in a sense, that's a constraint. So you need some kind of Lagrange multiplier to enforce the constraint. So that multiplier essentially plays the role of gauge field. So I think that will be plausible understanding of your origin of those fictitious or additional U1.
Yeah, that's very good explanation. Yeah, thank you. Yeah, that's exactly correct. Thank you very much. Okay, so but Sanjin, this U1 is extremely trivial. It's just if I have some operator.
It's trivial, but the if no, it's okay. Just because of chi, we don't know what that is. So maybe we can introduce extra U1 for chi.
Yeah, you can, because I mean, you know, if you multiply this thing by a phase and this by the opposite phase, you still get S. It just drops out of this construction. And so that's also why only chi transforms under the symmetry and not psi.
Yeah.
I didn't in this equation.
I
don't say
accept.
anything
I
about
accept.
Yeah, okay. Okay, so maybe we should have a thanks for all your questions. They are very good, and I hope I will give more answers in the next hour. So I understand now we make a 1 hour break and then we come back.
Yeah, thank you so much for the very interesting talk, and
Thanks a lot, Manis.
thank you for all the questions. And so we will come back at 6:30 Korea time and 10:30 Europe time.
Okay, thank you very much. See you soon.
See you
Yes.
soon.